Okay, good afternoon, fellow foundrymen. Let us start today's program. Before we get started, we request all the participants to put your microphones in the mute mode so that no, we will not have any disturbance during the presentation. You may unmute yourself end of the session and to raise your questions, or you can put your questions in the chat box. I request everyone to cooperate. And it gives me immense pleasure to interact with you all for yet another webinar, which is being conducted by Chennai chapter. And this initiative started from our last tenure, and we have been continuing this. To get things started, now I request our chapter chairman, Mr. Raman sir, to welcome the gathering, please. Raman sir, over to you.
Yeah, thank you, Sandil. Okay. Dr. Sir, welcome you.
Thank you, sir.
For this wonderful webinar. Thanks for coming to Chennai and agreeing for this presentation. On behalf of Chennai chapter, Institute of Indian Foundrymen, I welcome all the fellow foundrymen for this webinar to be presented by Dr. Anjan Prodhan, ex-scientist. Anjan Prodhan, ex-scientist, CSIR-National Metallurgical Laboratory. And today's topic is a very different topic from the usual one. So where we are going to enhance our knowledge on two different topics, namely degassing of molten aluminum, copper and iron alloys using electric current treatment, and semi-solid processing of metals alloys using electric current treatment during casting in a sand mold. So definitely these two topics are different from the usual webinar which we were conducting for the past 1 year or 1.5 years. I thank Dr. Anjan Prodhan for his personal interest shown to us to deliver his knowledge to all the fellow foundrymen through this webinar. I request all the fellow foundrymen to attend this program fully, and you can raise your questions at the end of the program to Doctor, and Doctor will be in a position to give the explanation and the answers at the end of the program. So now I request Senthil to take it further, and he can introduce the doctor to the forum. Thank you.
Thank you, sir. Thank you very much. Okay, fellow foundrymen, once again, thank you all for participating in this webinar. It is my immense pleasure to introduce our speaker for the day today to all the audience. See, Dr. Anjan Prodhan, as chairman said, is all the way as he is live in Calcutta. He has come for Chennai for his personal work. He has take his time to spend for foundrymen to share his knowledge. It's a great, and thank you, Dr. Sir, for your great initiative. Generally, people used to keep the knowledge with them, but you have come forward to share your knowledge. It's great, and it will definitely help the foundrymen. And Dr. Anjan Prodhan is ex-scientist. He's completed his B graduation from Bengal Engineering College, Howrah in 1982. Then he's done his MTech from IIT Kharagpur in 1984. Then subsequently he's completed his PhD from same IIT Kharagpur in 1988. Then subsequently he has joined CSIR-National Metallurgical Laboratory, Jamshedpur in 1988, and then retired from the same organization 2022. Almost about 34 years worked in the same organization and in the research organization. You can imagine the in-depth knowledge he must have spent his whole career in the research. And I'm sure that we'll be getting benefit out of this knowledge. And he has contributed several technical papers in national and international journals. And he has got about 4 patented processes in his name. And he has participated in different type of in-house and sponsored projects. And he has formulated and executed sponsored projects from DST and DRDO. And let's hear from Dr. Anjan Prodhan about new process, and let's enrich our knowledge. Dr. Sir, the forum is yours. Please take over.
Thank you, sir. First of all, I said thank you to give me the opportunity to share my knowledge with the foundry fellow from the Southern chapter of Indian Institute of Foundrymen. I was associated in IIF for a long
It's our
time.
pleasure,
In
sir.
Jamshedpur, I was the secretary of this chapter.
Oh, that's
Later,
great.
right now, I'm also in the editorial board of Indian Foundry Journal. From the journal side, I will
Okay.
request to share their technical papers to the Foundry Journal. Every time Mr. Dural Babu is chasing me, sir, give some paper to me. We have lack of papers
Okay.
and we have shortage of paper. So from my side or from Foundry Journal side, my
Okay.
humble request to all of you to share technical papers, real life problems, and it will be
Definitely, sir.
useful for to share knowledge to all the founders across the India.
Yes, sir. Yes, sir.
Yeah. Thank you once again. Thanks to, I shall good afternoon to all the foundry fellows. And now I am sharing my knowledge, whatever I gain to doing work at CSIR-National Metallurgical Laboratory for so many years. First slide, I can show it, famous Albert Einstein's vision. Imagination is more important than knowledge. Knowledge is limited, but imagination encircles the world. From my perspective, research is a blind man's perception on an element. So we are all blind who are doing research, and if you were to find out, we predict many things, but we reach the total amount of, total mass of the problem or total. So then we can share, make small articles and share our ideas, but to gather make the totality is a very difficult task. Suppose it was scientific research. You see, scientific we can several terms are available: thermodynamics, kinetics, phase rule, physics, chemistry, metallurgy, solid education, electrofluid dynamics. So many typical avenues are there to deal with in the science. But science is not all. You all technical people, so you will interested for technology. And if you go for the technology part, there are several another factors are there. They have to start with concept, then process feasibility, then whether the process is environment friendly, whether the process is cheap, whether humans can adaptable very easily. It will be low investment cost, low maintenance cost, and early return on investment. These are the all factors, and there are two groups of people who are favoring technology and another group favoring science. There are a lot of conflicts, so we should minimize the conflicts. So my request to all to make hands to join each other to minimize the missing link, missing concepts, so that we can do something better for our country. Now I shall share some new methods for the foundrymen. My address is there. You can note down my email address as well as telephone, so the telephone numbers, so that you can share your queries and separately, so that I can respond to you properly. Actually, my feelings is if I interact more, so that I can know the problem from the basic problems from the industries, so we can upgrade or update myself, and we can do something better for you, so that all will be benefited. Second is I shall make the your acknowledgement. So from academic sides, I've got support from my family members like Dr. Achinta Kondandi, who is the faculty of neurology for the Medical College, Kolkata. And the electric current treatment is basically I've taken from him, because electric shock treatment is people are know medical science. It is a known factor, known field, but in metallurgy field, this is less used, but later people are known. Not available. Secondly, Professor Devijan Khan is in faculty, a nuclear physicist, faculty at IIT Kanpur. He gives some basics of theories or hypotheses. He helped me to develop this type of hypothesis, so I can share it with you. Then industry, my uncles are there, Professor Mr. Ajay Kumar Nandi, he is with MIMC Durgapur. Mr. Amal Kumar Pal is in an iron and steel company, foundry division, Kulti. And that's why I've been infatuated on the foundry side. And for DRDO side, Dr. Shashi Bhushan Singh, he is DRD. He helped me to lot during my aluminum silicon carbide composite machining trials. He helped me a lot, and he used his premises to give me the composite making at the laboratory. Finally, financial support I got from Department of Science and Technology, Government of India, and DRDO, Defense Research Development Laboratory. Financial support I got. And industry, degassing trial, I got support because I was associated IIF Jamshedpur chapter, where I can get support from Saha High Tech and Automotive Casting to carry out industrial trial at that end. Then in Delhi, Century Metal Recycling Private Limited. Then in Bangalore, Rafsi Industries Private Limited. Tata Steel nearby, our company, I mean institute, Tata Steel. And for semi-solid processing work, white and brown alloy casting Kolkata, set and iron foundry Howrah, and aluminum silicon carbide composite machining trials, vehicle research and development institution at Ahmednagar. My content is electric degassing of molten aluminum, copper, and iron alloys, semi-solid processing during sand casting with electric current treatment, machining of aluminum silicon carbide metal matrix composite, and removal of zinc and iron from molten aluminum. Today, I shall try to cover part A and part B right now. From hypothesis to production, electric degassing of molten aluminum, copper, and iron. This is an alternative to Seward's law. As I mentioned, Saha High Tech aluminum casting, Jamshedpur, we conducted trial at 200 kg, Century Aluminum Recycling Private Limited, Delhi for 800 kg, and copper is successfully implemented at Rafsi Industry, Bangalore on 100 kg scale. And iron, Tata Steel, Jamshedpur, they extend their support in the laboratory for trial on 25 kg. And this is the certificate I received from Rafsi Industry, Bangalore, for doing their work on degassing of electric degassing of copper at their end. They are making electrical contracts and they're exporting them. The conventional method of aluminum degassing is aluminum. Why degassing? Molten aluminum loses the hydrogen solubility drastically at the melting point. Here, it drastically there is solubility Cc and per 100 grams, soluble at 8% hydrogen. That's the convention. It is ppm plus 1 ppm, 10 ppm, then 100 ppm like that. During the melting point, on the freezing, that solubility hydrogen drastically lost. That's why the hydrogen remains at penal gas porosity unless it is removed from the melt. It iterates the mechanical properties of casting. How the degassing methods? Vacuum treatment or purging by nitrogen or argon gas. Argon gas is costly, so commercially vacuum is also costly. Commercially, dry nitrogen is being used for degassing. A degassing mechanism like that, you purge with nitrogen, place nitrogen here. All the hydrogen is soluble, they cannot come out easily because of the hydrostatic pressure of the molten metal. If a nitrogen bubble are injected, then hydrogen joins the nitrogen bubble, then gradually floats up and bursts and are then exposed to the atmosphere. And some of the inclusions are removed by using argon gas. And there are rotary degassing processes used. There are lateral size and different size, and there are different type of compositions are available, and treatment times are given here. It is all data received from the FOSEPO, hydrogen content before and after degassing, and the efficiency of rotary, the various degassing but bubble size. It changes from rotary, then porous plug, and lancing, and tablets. Tablets is acceleration treatment, I mean degassing treatment. Then nitrogen gas, then another. Suppose these the rates on the hydrogen atom dissolved in the melt, then nitrogen inert gas bubbles are here, while during floating, it comes and picks up the hydrogen molecule, comes up and upwards, and finally it is reached to the top level and exploded and remove the hydrogen there. The operation in a rotary degradation, POSECO MTS 1500 degassing unit. That rotor is there. It is inserted and rotating at particular speed. And some is rotating, but we are producing a lot of aluminum dross during the operation. Dross are there. Drosses are there. That is the main drawback. You can do the degassing, but you also generate aluminum oxide dross plenty during the process. Then you have to define the how much the rotation speed in that gas flow rate to 20 liter per minute. If we change the rotation speed, then 550 for 6 minutes is the optimum time here for a particular alloy, aluminum, silicon 7, magnesium, the LM25 group of alloy. By increasing rotation speed, the power is increased and degassing performance is improved. For every rotor treatment vessel combination, there is a speed above which further increase will not be improved the degassing efficiency. So that's why we have to restrict the time of degassing, purging, and flow of metal or form of gas. Then alloy composition is going to also depends on variety of alloy composition. That factor is there. The presence of certain alloying elements increases the decrease solubility of hydrogen. Magnesium in alumina alloys has a major deleterious effect on degassing ability. There is tremendous loss of magnesium, around 30% or more, by this gas purging. Now, this process treatment cost is there. Because the cylinder of contains 7,000 liter nitrogen. Now, see, it is a rough estimate. Then for 600 kg bath, 20 liters 6 minutes. So cost is around ₹3. But electric degassing by electric current, the cost is actually established in next slides. Assuming the cost rate of electricity is 10 rupees, its cost is around 40 paisa or 0.4. The new method, the hypothesis is like that. The melt is ionized by applying direct current DC, not AC. Nowadays in our rooms, I mean, the common say it is the DC supply into a molten bath. Hydrogen ionizes to hydrogen plus at anode. The hydrogen ionized here is anode. I am showing the DC supply as a battery. So anode at the bottom of the melting pot. Hydrogen being lightest ion, it will first act as a major charge carrier. It will immediately move to the as an ionic form to the cathode, anode to cathode. That is a negative charge point. So hydrogen being lighter will pass a major charge carrier. Aluminum also present here. Aluminum also there, but due to lightness of hydrogen, it will move faster than aluminum. Hydrogen moves towards the cathode, and at the top, DNA is there. Hydrogen, DNA is there to make hydrogen. Hydrogen, then atom, then hydrogen combines to one molecule. A molecule will form gas. Here, the metallic static pressure is less compared to the total bath, so that you can go up and explode that and it goes to the atmosphere. Towards the cathode, the deionized hydrogen forms molecules and subsequently to find bubbles. The bubbles then release to the atmosphere due to the low metallostatic pressure at the top of the bath. Then our results is hydrogen ppm and purging by nitrogen. Hydrogen pressure falls like this while purging with nitrogen, and the nitrogen purging like this. So 0 to 50 like in 15 minutes time. It is a laboratory scale trials, 5 kg melt. It's electric current treatment. See different commercial aluminum, LM25, LM6 eutectic aluminum, then power consumption. Power consumption, it is on 5 kg based melt. Power consumption gradually increases here. Then energy requirement is 10 to 20, around 25 watt-hour like this in 15 minutes time of purging. So aluminum level, hydrogen ppm level falls from these to this level. And the aluminium, then LM25 was like this. LM6 eutectic alloy is not significant. Trial industry level, so high-tech aluminum casting at 200 kg melt. We tried at two levels of power. One is 250 watt. The alloy is LM24 alloy. It is conducted in the rainy season. Critical that the rainy season and winter season, that the results are different because of the humidity factor of the atmosphere. Here you see the hydrogen level falls like this, falls, and after some time, it will picked up. I don't know why it is so anomalous, but it is picked up. That is some cutoff point. Similarly, if you go the mechanical testing, UTS, it is increasing because the loss of hydrogen go up to certain point, and after due to pick up of hydrogen, it again falls. So if you cannot conduct the degassing treatment beyond a certain point, this is conducted in rainy season, so the level of hydrogen ppm is showing more. But it is conducted in the winter season. First of all, this one, you can conduct same way. The UTS gradually increases, hydrogen gradually falls, and after 6 minutes of time, it may be 5 minutes also, because the scale is 4 to 6, it may be 5 minutes also. 6 minutes of time, we get the minimum, then again it is increases again. I mean, hydrogen increases again and mechanical property drops. But the fact is, if you do the, hydrogen and left the bath open for several hours, it is around after 3 hours, 180 minutes time, the hydrogen again picks up. Hydrogen picks up. Again, picked up, so that you can again you have to do the degassing part. You have to do the degassing part again, and again the same pattern follows. Similarly, UTS value also. So you have to be careful. If you make the hydrogen degassing, but you will leave for infinite time, again metal will be picked up hydrogen from the atmosphere, provided it is not covered by coronal flux. And again, you have to need for some further degassing to get the optimum value. Now the energy consumption and time. So we have done at power level of 250 watts and 400 watts. The energy consumption was from 42 watt hour to around 40 watt hour. If you increase energy with that optimum energy level, you can reduce the energy and as well as time of degassing also. This is all based on 200 kg melt. Now, Century Metal Recycling Delhi, they allowed me to do some trial on 800 kg melt. Their data is like this: degassing time more or less 10 due to rotary degassing process, and our case is 10 to 15 minutes, but it need to be optimized by 2 trials. Degassing medium nitrogen gas, DC current, and the melt temperature for treatment 740 to 750 degrees centigrade. Nitrogen consumption 200 liter approximately. Here no nitrogen consumption. Filtering of the melt not required, but here for the electric degassing process, you have to remove the electric and dross produced associated with the molten metal. Because you cannot filter it, I mean remove it. You cannot produce as well as you cannot, if you take the metal that in a melt, it will not work properly. Flux coverall is required, but flux coverall is not required for electric degassing. Electricity consumption kilowatt hour is for the rotary degassing, the motor to rotate the graphite rotor, that is this amount, and for our degassing purpose 0.5 kilowatt hour. The graphite consumption through rotor, there are around 400 heats, but our case only you are doing right on negligible unless you break it by accidental. It's negligible. Aluminum oxide dross formation is significant. Rare is nil. Temperature loss during degassing is around 25 degrees centigrade. In our case, 10 to 15 degrees centigrade. Density before degassing 2.54 to 2.57. Density after degassing for rotary degassing 2.65. For our case, 2.63. It is very close. Density of solid aluminum 2.6, 2.7. The process efficiency we calculate based on that, the 98.15 or 97.4. Pollution problem due to aluminum dross. There is no pollution, no dross is formed. Appearance or top surface of the vacuum, top surface of vacuum they are doing so phenol porosity and signature of exploded bubbles. So tiny entrapped gas bubbles and phenol porosity. The top surface of sample casting. The rotary degassing using coverall flux. There is some small bubbles and phenols are there. Here, lot of bubbles are there, and they are basically entrapped in the film of the aluminum oxide. In place of coverall flux, aluminum oxide cannot be formed, but here we are not using any coverall flux. So these bubbles are there, it is entrapped within the top layer of aluminum oxide. Some bubbles are exploded, the phenols are there, and that's all. For X-ray imaging, see, it is untreated, a lot of bubbles, and it is being swollen up. So, and partially, these white patches are containing gas. Bottom it clear. These dark patches, white patches are containing gases. Almost, I mean, it is equal. And that's fully degassed sample. These are cones are there. Depression is there. That is indicating it is fully degassed. Now, case of the rocks industry, degassing of molten copper. Molten copper and oxygen, they form copper oxide, but it is a reversible process. So electrical conductivity and density varies on the amount of oxygen present in the copper casting. And undegassed copper casting shows 70% of ISCS, International Annual Copper Standards. Fully degassed copper casting around shows 95 to 100 ISCS. Oxygen present in the melt both dissolve and are combined form, as I mentioned here. Due to dynamic equilibrium, copper liberates more oxygen during freezing. Whatever copper oxide there, during freezing, some part of oxygen is removed, and it is. So whatever, suppose you melting point is 1078. So at 1100 degrees centigrade, the density of oxygen available, free oxygen available in melt, they come on. It will go for further increase the temperature. The free oxygen level is decreased, so that if you do degassing at higher temperature, you can remove lesser amount of oxygen. If you go do the degassing at a lower and lower temperature, lowermost temperature, it will go maximum amount of oxygen can be removed. The remaining oxygen, which it cannot be removed, remain dissolved and remain liberated during the freezing, and this causes some porosity problem or cracking of the casting. The setup is like this. The graphite rods are there. They are inserted in the molten metal, the molten bath here. It is the holding furnace where 100 kg melts are being kept, and after degassing, that small components are cast in die casting. The weight of the casting varies from 2 to 5 kg, like that. And trial on 100 kg melt, you can see energy level varies from varying cost, like that. Time of degassing varies like that. Number of component cast and number of person rejection. Initial trial, we can optimize like that. So 15 watt of energy and time of hardening, and you achieve the rejection level of minimum out of this level. So what happened after that? That they are doing the practice with their laborers, their operators, so that rejection part is further reduced and is on below 7 to 8% or less. But that is human practice. Unless you do my practice, it is the experiment level with my done in my supervision. After that, they do their practice and they train their people. So then percentage rejection is reduced less than 10%. The treatment cost is like the decreasing cost of 300 kg male we are doing in the air induction furnace with the 300 kg capacity. The cost of electricity, the decreasing there in the induction furnace, they're passing with nitrogen gas for 20 minutes and in the with furnace power on. That's suppose you are consuming 35 kilowatt hour costing 350 rupees. Then cost of nitrogen gas 20 minutes for 20 liter per minute, around 400 liters, total 10 rupees, around costing out 360 rupees. Degassing cost of 100 kg melt in electrical treatment and holding furnace is 15% only. Electric degassing trial in the molten steel, it is Tata Steel with the support for doing conducting trial on 25 kg melt. And here the induction furnace, we are mainly melting the 25 kg melt, then pour into the sand molds, and the treatment was done in the sand molds. Because you cannot melt the degassing trial in the induction furnace where the molten metal is contained a stirring mode. The bath should be static, otherwise it cannot be useful. So oxygen present in a trial in a mold, oxygen present in the mold, both dissolved and combined form. There are two types of combination there, FeO and Fe2O3. Normally, it is removed by that oxygen present, aluminum or silicon or ferrosilicon. During degassing with aluminum is formed, whose melting point is 1818. It is almost a refractory material, and this causes the nozzle blockage during tapping from the ladle. The removal of hydrogen from molten iron by electrical treatment also reported by the Sandega, Kiev Political Institute in Ukraine. They can give this type of phenomena by changing the polarity of the electrodes, positive electrode pole and negative electrode pole. Then accordingly, they are also reported. A trial on 25 kg male during feeding a sand mold followed by welding an induction furnace. It is tested in the Tata Steel. Both were tried, nitrogen and oxygen, both were tried. Initially, our material is mild steel. Then mild steel, then we add iron ore to increase the oxygen content of the melt. Then mild steel, iron ore, then treated with electric current treatment for 45 seconds and consuming 1.5 watt-hour of energy. Then mild steel, and mild steel with electric current treatment without adding the iron ore, and it treated for 150 seconds and consuming 6 watt-hour of energy. So here, sample 4 and 5 can follow like this. Mild steel original sample 1 is like this in this range. Then you can see the removal of nitrogen removal is changes like this. Sorry, and oxygen content like changes like this. Sorry. So without presence of addition of iron ore and with addition of iron ore, without addition of the things are working, and you can remove nitrogen as well as oxygen, and when we remove from the molten iron bath. So first part, I can conclude with a statement from Travis Kalam. Don't take rest after your first victory, because if you fail in second, more lips are waiting to say that your first victory was just a luck. So this is the first part of my presentation. If you have queries, you can do it now or later after presentation of the second one. Now these, you tell me.
Sir, we can do it on after second session, sir.
Okay, sir. Okay. Then continue
That
for
would
the
be
second
better.
one.
Yeah.
Okay. No
Yeah.
problem. Because two different type of ventures are there. That's why.
Yeah. Okay, we can ask audience. Audience, if you have any queries, you can put forth
Any
now.
queries? Any queries related to the first topic? You can unmute and ask the question. Otherwise, put it in the chat box.
Okay, sir. So let me continue the second part.
Okay, yes, sir. You can start, sir.
Oh. Next is sinusoid processing during sand casting with electric current treatment. And it will introduce a new concept, thermoelectrodynamics. So comparison of casting process, we have advanced level, casting, thixo casting, then conventional casting. Conventional casting separate processes are there. Casting, you see, liquid is hold in a particular liquid and solid zone to generate certain fraction of solid, and this immediately casting in cast in a metallic die mold and to get the refined structure like. And thixo casting is a two-step process. Pellets are cooled to room temperature, then reheated and kept in a semi-solid state, liquid and solid zone, and again cast immediately in a sand mold. I'm sorry, shell mold or die casting mold. But conventional casting, there are so many avenues are there, and most semi-solid sand casting and is the most defect-prone area. And most of the people are doing sand casting, but they're very much also facing a lot of problems during sand casting. And my domain of work is the use of electricity treatment during sand casting only. And it is effective when the metal is in semi state between liquid to solid. When it is fully solid, it is a no effect, but the process will take place during the semi-solid state only. The advantage of semi-solid processing of metals, advantages that so many advantages are reported in the literatures, and people are almost know of this. So I'm not repeating. Actually, this is already published in my journal and IIF journals. You can consult in my literature so that you can read it. But several disadvantages are not less. Casting, so many disadvantages, and thixo casting, there is so many. It's very difficult to maintain the temperature. Furnace temperature fluctuation is the main problem. And melt superated to prevent freezing metal transfer system when press melt is added to the holding furnace, temperature remains well above the liquid. So it is impossible to keep the temperature at an optimum level. And like this, there is so many problems are there, thixo casting problems. And if you do in electric current treatment, I have some comparison with or friends and whatever report I have available to me. The weight of metals like this, and here is specific total specific energy consumption for this process for the electrical current treatment is least among all the reported literature available. So that is from the literatures. I've taken references from recent advances from foundry camera. The dendrites are there. That has been refined by automatic stirring, and this like that. This forms a globular like this. And it is from Journal of Metal Casting, published in 2009. You see the dendrites are there. It has been refined by electronic stirring. And our work is well patented. The dendrites are there, refined. But you increase power further, there is optimum level, it is getting coarsened. So we have to select how far power will be given to get the refinement. Refinement is there, it is low cost process. Laboratory melting and casting process, that is induction furnace is there, and pour in a daddle, and it a mold is there connected with electrical power, so that this is the wire is showing here and on from the bottom. Previous study at our laboratory source, the typical cooling curve. It was published in 1997. So typical cooling was pure aluminium, commercial pure aluminium without any field. We undercooled to 650 to 7 degrees centigrade and superated to 660 degrees actual melting point. Then phases like this. And see that time, you can make a time. And if you go over electromagnetic stirring, if the material in a solenoid field, and then it is undercooled, but more or less remains same at the same temperature, slight difference. Then it is solidified. The time here and here more or less same. But you could do with the electric current treatment, the energy consumption is less, almost half. And again, it is the solvent takes over a range of temperature and solvent time also reduced. And you see the mechanical property with TS value and load and without any treatment with electromagnetic stirring, it is increased elongation as well as UTS increase. And with electric current treatment, elongation also increases and arsenic can increase further. So the effective electric stirring is more effective than electromagnetic stirring. This experiment shows. And why it is so? That a lot of aluminum oxide dross is not removed, just melt and cast, not dross are not removed. In presence of electromagnetic stirring, the dross become refined and is organized in some way so that we can get dross have been broken some areas so that we can get some improvement in the mechanical property. Here, dross volume fraction of dross is further reduced compared to other two states so that you can get further improvement of the process. So without doing any degassing, degassing as well as no removal of aluminum oxide dross, you can improve the quality to some extent. Now, after getting the fund from Department of Science and Technology, DST, we do some scientific studies and we do capture the soil data through data logging system. We take this type of molds and with the bottom graphite block is there. After pouring liquid in a molten metal in a mold, we can add the second electrode from the top. And in presence of that, we inserted two electrodes on top and bottom. It is 1/3 from the top and 1/3 from bottom, or reverse is 1/3 from the bottom side, and so the two electrodes are thermocouples are inserted at the middle of the casting to get the monitor the temperature profile. And profiles are like that. It's published in 2001 Material Science and Transactions. You see, top is blue and bottom is red. A lot of fluctuations. So without electric current treatment, lot of fluctuations. And then B is low intensity, then medium intensity, intermediate intensity, high intensity. So these see the changes. Here the cooling pattern are separated and the fluctuations are reduced further in increasing the intensity. And in an optimum case, I shall call it optimum, the top and bottom are being merged together. You see top, the here 45, this is 40 diameter and 35 diameter and 30 diameter. So metal at 40 millimeter diameter merges with 35 millimeter diameter. This is the unique things or observed in the solution curves. But when you increase the power, again the undercooling is reduced and it will heated up and up to this point. So then and again the fluctuation increases. So what is your interpretation? Nothing but these fluctuations due to presence of hydrogen atoms. The hydrogen atoms that vibrate against some called tips, some called tip points, and this type of that also generates some millivolt or like for energy voltage, and this gives you the fluctuation. It is all taken by the data logger system. So the accuracy is more So these type of gas fluxes. Here the gas is being removed, removed, so that it is fluctuations are less, and then it emerges a total temperature difference between the top zone of the thermocouple and bottom zone of the thermocouple to matching together. Further, if you increase the power, electric power, increase the turbulence of the metal, and that will entrap more gases, and this type of fluctuation again will get. So there is some optimum value, particular size of casting, so you can get the optimum best results. The question is that is DC. When you apply the AC, the situation changes. Can you see a low current without degassing? A low current without degassing, top and bottom. Then if you see more gas is more fluctuations. The temperature is giving in millivolts, it is deflecting the temperature. So don't confuse. Actual temperature is not fluctuating in that level. It's the millivolt fraction of the thermocouple reading is reflecting over here. That is why millivolt generator, it's a fluctuation of hydrogen on the thermocouple tube. Top level, the upper level, upper 40 millimeter diameter thickness is there. Here the 35 millimeter, the fluctuation like this. Then is low, medium, and high intensity. Low power, which is low fluctuation. Medium power, medium fluctuation, and high intensity fluctuations are more. So in presence of gas, in presence of no gas, but with increase of electric power, you can change this type of thermal profile. Cross sections of castings with acid treatment, you see with full degassing, you can get the center line shrinkage at the top part of the casting, where the thermocouple is set at 40 millimeter diameter. Then 1, 2, 3, 4. When increase the intensity of current, you can get the porosity here. What is the optimum zone? It is mostly free from gas. But if you increase power, you can get also porosity is again coming back. These are thermocouple sheath inserted during the thermocouple sheath inserted during thermocouple sheath. And microstructure is microstructure, refinement, columnar structure, broken, then fully equipped, and it's again columnar structure coming back. Same is DC, but DC you can add the amount of power is more compared to AC. The same phenomenon happens over here, but here power will be requirement is more. Here also degassing, equates grains are coming here. Here also, and it's all columnar, and again sink is also coming at higher power, treated with higher energy. So LM6 alloy, how it is changing, that is a utility alloy. You see primary crystals of silicon crystals are there, and it has been refined, and porosities are there, and porosity are reduced with treatment. Secondly, it's been refined, structure is also refined there. If you go for higher casting, higher dimension casting, you see the without current treatment, surface is flat with current treatment, treatment. There is some shrinkages in here. There is more shrinkages here without. That means that shrinkage indicates that extent of gas removal is more over here. Another test casting is made like this, and it is cast or a section in this zone, and this is AC and DC current treatment. Now, how these things are changing without any current treatment, you can get internal shrinkage like this. with AC current treatment at minimum value of treatment, you can see the bottom, right? No, sorry. You can see the lower level part with minimum amount of current, or it is optimum case. So it can free from internal sinkage. Here with increasing current, the sinkage are again coming back. But in DC, sinkage remains there. You cannot have a sinkage in if you treat with DC. So why not treat with AC is the optimum case. Now there is some interesting phenomena over here. If you treat with AC, their internal sinkage is showing. The surface is more or less smooth. That indicates the entrapment of gas in that region. But here in DC, the internal surface is showing the roughness. That means that roughness tips, that is the tips of dendrites. Gas are being removed. The dendrites of tips are there. That is showing in this zone. Discussing another dimension, it is almost one scale is there. It is cannot visible properly, but 25 millimeter diameter scale with increasing current intensity. See, at lower level, all internal sinkage porosities are there. You can avoid it, but at optimum level, 2 ampere AC, you can get full, almost free of internal sinkage as well as porosity. But if you increase further current, then again it's coming back. So there is the optimum value. Now with support from white and brown alloy casting, we are doing trials at the industry with a 7-inch long casting with 1-inch wall thickness. And we make this type of casting and cut from this section, top section. The intention is that all the defects will be concentrated on this top region, so that you can cut top piece and again recut this piece, and these samples are shown over here. The 0 is without current, and 2, 3, 5, 5, 6 are barrier with increased current and different level. The basic interesting thing is with 0, where current was not treated, the inner side of the casting shows the more shrinkage than the outer side of the casting. This is the outer side, because during casting, the outer side is get detached from the mold wall, so the thermal, heat transfer rate is less at the outer side compared to the inner side, and inner side gets stick due to internal shrinkage. Shrinkage, then it gets adhered to the internal core side. While you treat with electric current, see both sides are rounded, because both sides are detached from the mold wall during casting, and solidification takes place without in contact with the mold wall. It is separate from the mold wall and solidify. All the electric current treatments showing the same result, and extent of shrinkage is reduced. Now you can see the microstructures like that. The hydrogen level is 3.1 ppm, so a lot of gas porosities are there, and with current treatment 2, 3, 5, 6, hydrogen is minimum at 2. Then I can further increase the current, hydrogen increases gradually, and more porosity is appearing at with increased current treatment. So there is the optimum value. I want to send the message to you that you can get the minimum level of gas porosity or maximum efficiency of the process. Then sand sticking phenomena. Sand sticking phenomena, you see the core side, there are a lot of core side of the casting, a lot of sand sticking is there. Then the surface of the casting, there is mold wall, it is metal is detached from the mold wall due to shrinkage. No sticking outside surface, or there is little sticking over here. But while treating with electric current, no sticking on the inside surface, no sticking on the outside surface. That's why I want to mean that total solidification takes place without any support of the mold wall. There is some bands are there. Seen typical bands appear in casting surface when treated with electric current. Typical bands are there. But the unique phenomena I've observed, but on my side, I've tried to establish like this: molten metal, mold, and molten solidified metal in normal case, conventional solidification. But when electric solidification, the solidified metal is separated from the mold wall. Then molten metal will remain over there. Then another batch of that solidified metal set over here, and that's therefore they're making this type of bands like that. But it is actually visible at a particular level of current intensity. But if you go for higher current, this is not appearing. It is finished. Now this treatment is done in the stainless steel, and while casting, there are a lot of gas porosity is there, and small metal model surface is tremendously affected. But with treatment with electric current, you can see the changes over here. The total surface is entirely smooth, and it reduces the metal mold reaction. So that for fettling aspect point of view, still improving the fettling efficiency. I mean, cost of fettling as well as time factors. In case of head mill magnet steel, it is properly problem is the formation of this type of carbides. Those carbides are formed. They contain 12 to 12% manganese and 1.1 to 2% carbon. That carbides are formed so that manganese with its own importance, but you can at such condition you cannot use it. Then you can try with low and high intensity current. You can find the volume fraction of carbide has been reduced. That will reduce with increasing intensity of current. That is a unique phenomenon observed. But here is the embedding interconnected carbides manganese steels from during slow cooling radiating through 400 to 800 degrees centigrade. The removed dry solution to annealing to 1000 degrees centigrade followed by rapid quenching. This is very important. We have to heat it. The kinetics of carbide formation follow a typical C-cup or isothermal transformation diagram with the fastest growth carbides occurring at 600 to 650 centigrade. Essentially, two types of carbide form. The thin carbides form very rapidly and appear as grain boundary. That the thick carbides nucleate on thin carbides and grow along the grain boundaries. The thin carbides do not embrittle the steel significantly, whereas the thick carbides embrittle severely. The latter are distinguished from the thin carbides by having resolvable cemented interior with a cleaner austenite carbide interface boundary on the both sides of the cemented frame. Heat treatment cycle, the very most important part of the head mill magnet steel. They cannot insert directly into the 1000 degree centigrade level, but you have to make the steps. Unless you follow these steps, if you pour directly, the casting will crack immediately. Then you soak for a particular time, depending on casting geometry, casting section thickness, then quench it immediately. But if you adopt our process, you need to reduce the volume fraction of carbide phase. You can insert directly at a higher temperature, so that thermal stress will be less because volume fraction higher due to higher volume fraction of austenite phase, then it will absorb the thermal shock. So you can reduce the thermal cycle drastically, but I cannot do it in an industrial scale. But laboratory scale, we tried it and it succeeded. So industrial trial is pending for this study. So you can cover it and you can do it homogeneous treatment, and that it reduce both time as well as energy consumption. Can be done over there. Second part is copper nickel alloy, 50% nickel. It is very prone to coring effect, and you cannot remove the coring by treatment at 900 degrees centigrade for 16 hours. The coring remains same after dendrization. But you can do it in the electric current treatment. But mind it, the electric current treatment, all concerned are doing in the sand molds. not can be done in the metal mold because metal mold itself bypass the metal electric current so that it cannot be effective. Cast in sand mold without current and with lower amount of current, it is mentioned here. It can refine the because of the faster rate of heat transfer that is shown in the cooling curve earlier. Further, with increasing current, there is a breakage in the dendrites and it's finally refined dendrites. So energy consumption table is treatment current density or gradually increasing like that. Energy consumption gradually increasing. Energy consumption for homogenization treatment mentioned over here, 16-hour homogeneous treatment. They consume around 80 kilowatt hour energy. But here we can reduce the energy consumption further, and ultimately at this level that you did not do any homogeneous treatment. So we can reduce energy cost as well as time. Both can be done. Okay. And copper tin alloy, they are susceptible to interdendritic shrinkage and porosity. But when you use the electric energy treatment around 50 watt hour only, the interdendritic shrinkage is almost removed. But there is some portion there, the primary phase, it is the cracking of the primary phase. Solidified. After that, you do this peritectic phase over here. This phase is soft, so it can crack. But primary interdendritic phase are removed significantly. And porosity volume percent is reduced from 2.7% to 1%, but only at a cost of 51 of energy. It is done in the sand mode. And when you apply this in gray cast iron mode, the flakes are there. Obviously, you can see. Then you go to electric turbine, the nodules are coming up. And all the primary ferrites are there. And it is eutectic zone. That whatever eutectic, that can be converted to nodules. Energy consumption only one. Nodules of graphite flakes by electric current treatment during casting. Dissolved gases like nitrogen and oxygen are removed from the melt, which is surface active and prevent formation of graphite in the nodular. The removal of nitrogen and oxygen, I have shown you the earlier part. So hope you don't have enough. We are convinced that due to this factor, these nodules have been formed. And we had tried in the gray cast iron, in the set iron foundry, however, in the regular casting process. These are the all flakes with perlating matrix. And flakes have been removed, and you magnify it, and you can get some nodules will be found. But another factor is appearance of it is fully perlative, appearance of ferritic phase also. This white phase are ferritic, you can appear. So this not only changes the graphite from nodule there, this also changes the matrix also. It increases the eutectic composition to the left side, pre-eutectic. Electric current modifies the equilibrium phase diagram of, equilibrium phase diagram of iron and carbon graphite. So there are certain theories given by Ten and Monroe. The cupel element contains dissolved nitrogen gas of this level, oxygen and hydrogen this level, according to Goodrich. If a normally contains 70 ppm nitrogen in equilibrium, when the dissolved nitrogen increased over that flake, nitrogen is generally controlled by titanium. Normally, by chemical means, titanium is fixing nitrogen. At high nitrogen, titanium, the graphite structure will become a flake. 10 established the oxygen influence of the structure properties of cast iron. Oxygen initially present in the molten when chemically combined stage, but not have any significant effect on the cast iron crystallization. Besides graphite crystallization substrate and also increases the oxidation degree, the cast iron dissolved oxygen deactivates the potential graphite centers and increase the chilling tendency of the cast iron. At the same time, more cast iron saturated oxygen, the higher tendency for gravitation modification. These are metallurgy of cast iron out of harness fire. The tables are available. So Kolbasi, Upola, Cupola, then Cupola line, steam late part furnace. Then oxygen ppm, hydrogen ppm are listed over here. You can compare the levels. So to conclude, an optimum intensity electric current treatment eliminates internal sinkage in the casting. However, it increases current. Electric current treatment modifies flake graphite to nodular graphite in casting and also reduces paralytic phase without mechanism treatment. AC current treatment reduces primary carbides in high-field manganese steel, reduces metal mold reaction. It's a pollution-free process. It's more energy efficient compared to linear electromagnetic stirring or rotational electromagnetic stirring. Gas porosity is increased by increasing AC current intensity. DC treatment causes instantaneous sinkage formation, but AC treatment favors gas entrapment at the casting sections. There is a good similarity between optical microstructure current treatment samples and conventional semi-solid, metallurgy sample, semi-solid manufacturing samples. So I am concluding my presentation over here with a statement from Saran. You need to create simple yet effective system that makes ordinary people achieve external results. Thank you, sir. Any questions? You can.
Thank you, sir. Participants, any questions?
Hello?
Yes, sir.
Sir.
Tell me, sir.
Sir, one question is there.
Yes.
How does degassing and shrinkage in aluminum is related, sir? A whitish layer is appeared in the casting. Is it related to degassing or any other defect, sir?
Degassing.
Gentlemen, can you please introduce yourself? Your name
Sir,
and the
myself
company name.
Yogesh, sir. Yogesh, sir, from Rajmana Industries, Davaspeta, sir.
Okay, sir. Doctor, sir, please proceed.
In the degassing for the liquid metal, degassing is favored by DC current treatment. So you can method is the hydrogen is been ionized, or in case of oxygen is ionized, or in the nitrogen ionized, and that will move from electrodes from one zone to another zone, where the ions are moving through the molten metal, and it is go to from lower isostatic pressure, lower higher isostatic pressure region to lower isostatic pressure region, and remove from the gas. And for solid state, semi-solid state processing, it is favored by the AC treatment. AC treatment helps to remove the internal sinkage cavity at the optimum level. To go for higher amount, it cannot helpful. It will create porosity again. It is clear to you, or in on further clarification?
Shrinkage porosity, you're telling us, sir?
Yes, shrinkage porosity is telling, because the solidification pattern is also telling. If you want, I can make a sketch how things are happening in a piece of paper, and I can show it in the screen, that in this camera. Can this spare 2-3 minutes? I will collect one piece of paper, white paper, and trying to explain you what is the exact phenomenon.
Okay, sir.
Sir, we can send him the mail, sir. Maybe you can drop your mail, sir, and we can send him, or WhatsApp.
Sir, can you give your mail ID, sir?
Mainly, I have given in the past in the presentation slide. I can show you one second.
One second. Yeah.
Yes, there is my email address and telephone number is there.
Okay. Thank you, sir. I will mail you any questions, sir.
Yes. Any other questions, sir? And it is, I told you, the second part is thermoelectrodynamics. We are well known to thermodynamics, but electrodynamics is another phenomenon. But to tell you verbally, it is not sketch. I have to make a sketch. So basically, at the interface of metal and mold, The normal phenomena, metal will freeze at the mold surface. Okay. Then second part, when metal is frozen, suppose a particular instant that but the liquid metal just frozen. So solid metal and liquid metal are at same temperature. One is without latent heat, another is with latent heat. Liquid is latent heat and solid is without latent heat. The solid part is attached to the mold wall. Now, what electricity is doing? Now, electricity, the phenomena of electricity, you know, it will act as a passes to the surface of the cable or conductor. When the total molten metal is a conductor, that resistance is more. When a thin film of the solid phase is formed, now the conductor, the electricity, all the electricity will pass through the conduct through the solid phase. That's why metal mold cannot be used for this treatment. Do you follow my point, sir? You respond yes or no, sir? Hello?
Yes, sir. I think we can proceed. Yeah. Yes, sir. I think we can proceed.
That solidified part, the difference between liquid part and solid part is solid part is more conductive than the electrically conductive than the liquid part. So what electricity will do? Let's try to pass through the solid part. Very thin, when the very thin film, it is micron level or angstrom level thin film is formed. All the solid, all the entire electricity without flowing to the molten metal, liquid metal, they try to pass through the solidified part, and that cannot withstand the solidified part. Again, the solid part it will remelted and join to the molten metal. You follow my point? That is the typical phenomenon happening. It is given by my uncle, Professor Deviswaran Khan, faculty, nuclear physics, IIT Kanpur. That has been given, not given by any academician right now. That unique phenomena happens over here. The solid part immediately dissolved by the electricity. That is what thermoelectrodynamics. Okay, I shall make a sketch and try to send you.
Okay, sir. I think we can pass on to the people later, sir.
Yes.
Prasad, if no other questions, you can give a vote of thanks.
Sure, sir. So,
okay,
yeah.
Thank you, Dr. Anjan Prodhan.
Thank you, sir.
Thank you for sparing your valuable time and enriching our knowledge. So, thank you, participants, for attending this webinar fully and participative. So, likewise, IIF Chennai chapter is conducting webinars on every Saturday. The link will be shared in your concerned organizations. Thank you, sir. Thank you to all. Thank you.
Sir. And another 2 parties left, so that you can make time for
we can schedule it, sir. Yeah, we can schedule it, sir, and then we can communicate to the people.
Yes,
okay,
yes,
sir.
Yes.
Thanks, doctor. Thank you. Thank you very much. Thanks for participants. Thank you very much.
Thank you. Thank you for patience
Thank you, sir.
And if any type of problem later, you can mail to me so that I can update my knowledge also. And if you are interested to use this technology to proper foundry, you're welcome.
Sure, sir. Sure. Thank you, sir.
Thank you. And secondly, as a member of 8-year board Indian Foundry Journal, I would request you to contribute good technical papers for the foundry so that our interaction will be more.
Sure, sir. It's our pleasure.
Thank you, sir.
Thank you, sir.